Hello. So we're picking off right where we left off. You remember we went through saying what is a Turing machine? We see that you can cast it quite compactly and nicely mathematically as a seven tuple with certain elements, a set of states, two alphabets, and most importantly, a transition function. We looked at how you understand its execution in a kind of computer science way through pseudocode, and then at how you understand its execution more mathematically. And that was quite a few definitions, but unfortunately, I'm going to ask you to hang in there for a couple more. We're at a stage where we can say some more things that are going to be useful in the future, and we might as well say them even though we'll come back to them later. So we've talked here of the devices that perform the computing, but remember that the object is to solve problems, and we formalize these problems as languages. A language is just a name for any subset of strings over the alphabet, a subset of sigma star, and implicitly it captures a decision problem where you're given an input x, which is in sigma star, and you want to know whether it's an L or it's not an L. And so we've seen many examples. The first example is a set of all binary strings with first bit 1 and last bit 0. The second one is the Turing machines and inputs associated them so that the Turing machine halts on that input. It's the halting problem. The third one is the graph example we've seen before. So we have all these languages. And now we can start formalizing what we mean by solving them or solving this decision problem. The most basic type of solvability is what we call decidability. And this does the obvious thing. In other words, for any input, you have a program which will correctly return the right output relative to the language. So more precisely, we fix this language L. Now I'm handed a Turing machine M, and I'm going to say it decides L if for any input W that you give the machine, the result of the machine tells you whether W is an L or not. If W is an L, the machine accepts. And if W is not an L, then it rejects. Now, importantly, this has to hold for all strings in the language, in the alphabet. All strings over the alphabet. And remember that both accept and reject means that the machine halts. Usually, we will be given the language or problem, and it'll be our job to tell whether it's decidable or not. The question we would ask ourselves there is it possible to design a Turing machine which has this behavior, which decides the language? And that'll take some creativity. Maybe it's possible, maybe it isn't. In the cases where it is possible, we call the language decidable. So decidability is associated with an existential quantifier. There exists a Turing machine that decides the language. Now, as we've hinted at earlier, there are different notions of solvability. Decidability is kind of the most basic and natural. But another one is called recognizability, and it's a one-sided notion in the following sense. Again, you fix your language, and we'll talk of what it means for a Turing machine to recognize it. If that's the case, for all inputs to that Turing machine, where inputs are arbitrary strings over the alphabet, if the input is in the language, it's a positive instance, then the machine accepts, which is just like the condition here, no change. But the other one is a little different. What it says is that if the input is not in the language, then when you run the machine on that input, it will not accept. Now, at first glance, that sounds like another way to say it rejects. But the important or interesting element is that it isn't. Because Certainly one possibility here is that it does reject. But the more interesting possibility is that it neither accepts nor rejects. In other words, it does not halt. It just keeps going and going, and that's called looping. And that's the sense in which this is a kind of half decidability. If you don't know whether an input is in the language or not, and you start running this machine to tell you whether it's in the language or not, maybe at some point it'll halt and then you'll say, and accept, and you'll say, oh great, it's in the language. But maybe you just sit there and wait and wait and wait and nothing happens. It just keeps going. And then you don't really know, because maybe if you wait 5 more minutes it would accept, but maybe not. Why are we interested in this? Because it's a natural property of many problems, and it'll come up quite a bit. Again, we move to a higher level by talking about this property for a language. For a language to be recognizable, there must exist a Turing machine that recognizes it. Now, there's this further piece of vocabulary. We call a language co-recognizable if, when you look at the complement of that language is recognizable. Again, the complement of L is itself a language, so you can apply all these definitions to that set. If for that set you satisfy recognizability, meaning there's a Turing machine that does this, with L here replaced by L complement, then L is co-recognizable. Now, we'll look at all these in more depth later, both from the point of view of intuition and examples and so forth. But given that we had the vocabulary to define them, it was perhaps worthwhile to lay it out already. Similarly, it's worth saying what it means to compute a function. So remember that a Turing machine can not only accept and reject when it halts, it can have an output. The output is simply whatever it leaves on its tape up to the first blank symbol. More precisely, we'll say the Turing machine has output y, where y is a string, if its final configuration is an accept in which also the tape head is on the first square. Everything to the right of the tape head up to the first blank is the output. Configuration language, it would be written like this. And we might abbreviate this by just writing m of w equals y. Now, if we are given a function, this is some mapping that takes inputs in the set of all strings over the alphabet and returns outputs in the same set, we can talk of computing it. To compute it, I have to exhibit a Turing machine such that when I run it on an input w, it always halts and always accepts, and the output on the tape is the result of the function f applied to w. This has to be true for all inputs in the set of strings over that alphabet. Again, you go to a somewhat higher level by saying if you give me a function, maybe it's computable, maybe it isn't. If I want to show it's computable, it's my job to exhibit a machine M that has this property. Okay, we'll refer to these as needed. Okay, finally, let's try to design a Turing machine. Now, this is not something you maybe are going to do a lot, but somehow I think it's nice if once in your life you actually write a Turing machine program. If you don't do it more often than that, it's fine. We'll do it for a really, really simple language, which is the one we've seen many times, the set of all binary strings whose most significant bit is 1 and whose least significant bit is 0. So numerically, think of it as the binary representations of even numbers which are strictly more than 0. We can make a claim about this language in terms of what we've just stated, that it's decidable. So suppose our job is to establish this claim by proof. Now we can go back to the definition. What the definition tells us is, I need to exhibit a Turing machine that decides L. So it's my job to describe the full Turing machine. That means the set of states, the alphabets, the transition function, and so forth, in such a way that whenever I run this Turing machine on any input x, it will accept if x is in the above language and reject when x is not in the above language. Well, that's simply a programming task. Effectively, in the language of Turing machines, in the programming language of Turing machines, I'm being asked to write some code to solve this problem, to decide this language. And so you have to just think how you might do this. Okay, so we have this string x. From the Turing machine perspective, it sits on the tape. It occupies positions 1, 2 onwards. I don't know how long it is, but it's of some finite length. I need to scan it, and I need to figure out whether the first bit is a 1 and the last bit is a 0. This would be incredibly easy in a normal programming language, but this poor Turing machine will have to do a little bit of work. It's often convenient to describe Turing machines by state transition diagrams, so we're going to do that, kind of introducing them in the process. It starts in state Q0, that's the start state, so no choice about that. So at this point, we're scanning the first bit of the input. So what am I going to do? Well, if that first bit is a 0, then I already know that I need to reject, because I'm going to accept only if the first bit is a 1. To accept, of course, something else must be true, but if the first bit of 0 is 0, we need to reject. From state Q0 then, if I read a first bit of 0, I'm immediately going to go to a rejecting state and transition. That transition results in halting with reject. What does this all mean? Formally, the Turing machine instruction needs to say, when I read this, what do I write and how do I move the head? I don't actually care what I write and how I move the head, but I have to put something there. So what I'll write is just write the same symbol. You write move to the right. Another element of the Turing machine is that you have to kind of cover all possible symbols that you might be looking at. So I need to also say what happens if you're looking at a blank. What would it mean if at the first tape square I'm looking at a blank? Well, the input is the empty string. But the empty string is not in the language. It doesn't have a first bit of 1. So again, I will reject. Now already it may be helpful to say, how does this translate into an actual formal Turing machine description? We would have to write a transition function. We could write it as a table. That's often a convenient way. So what does this picture translate to in the table? Remember, the transition function says, given an input state Q, given a symbol sigma on the tape, what is the result of the transition function, meaning the state to which we transition, what we write, and how we move. I need to fill in this table for every choice of these two pairs. That would fully specify delta. I haven't done that. It's too much of a pain. But if you look in the beginning, it says if you're in Q0 and you read a 0, you transition to the reject state, write a 0, move right. That covers this. The next line covers this. Actually the third line covers that. If I'm in Q0, I read a blank, I move to the reject state, I write back the blank, and I move to the right. Okay, what if I instead read a 1? Again, and now I'm in state Q0, scanning the first square, and I read a 1. Well, this is looking promising. The most significant bit is a 1. So now I want to say, okay, I need to keep going. I need to figure out what the least significant bit is. But this poor Turing machine has to step by step now move all the way to the end of its input and look at that last bit. So it'll do this. How does it do that? It's got to keep moving to the right until somehow it knows, okay, I've hit the last bit. But how can it actually know it's hit the last bit? The only way it knows is that the symbol following that is the blank. So really what I'm looking for is a blank. And once I see a blank, I'm somehow in business. So how does this search for a blank go? From here, I transition to a state Q1. In state Q1, as long as I see bits on the tape, 0 or 1, I just stay in that state. And I keep moving to the right. It doesn't matter what I write on the tape because we don't really need writes for this problem at all. So I'll just keep writing back whatever I read. So this thing will just keep moving the head one step right over and over again as long as I'm looking at bits. When do you do something different? Well, at some point you'll hit a blank because you'll have read your whole input. At that point, this Turing machine gets excited and it says, I'm going to transition to another state, Q2. So now it's sitting in state Q2 and the symbol it's looking at is a blank. But it knows that this is the first blank I've seen. So whatever is to the left of that is the last bit of the input. I need to now go and look at that last bit. So how do I do that? Well, this transition here included this L left. So I write back the blank, but then I move left. So in state Q2, I'm now actually scanning the last bit of the input. Okay. Now, as we go along, we could illustrate what's happening with an example over configurations. Suppose I started on the input 110. The first configuration looks like this. This says Q0 is the state, the starting state, and the tape head is looking at this one, and here's the full input. What happens? It's a 1, so this transition is followed. I now enter state Q1, but I've moved to the right. In configuration language, the Q1 is written one step to the right. This one goes to the left because it's now to the left of the tape head, which is scanning this one. In state Q1, if I read a 1, I will move to the right and leave the contents of the tape unchanged. That'll do this. One more 1 has been traversed, and I'm scanning the 0. Scanning the 0, you again move to the right and stay in the same state. It now looks like this. From the configuration perspective, I'm scanning the rest of the tape, or the empty string, but I know that the meaning of that is that everything after this is a blank symbol. So now this applies. In state Q1, you're actually reading a blank. So you will transition to Q2. But due to the left move, your tape head is now scanning this 0 over here. You moved 1 left. In configuration language, it looks like this. Okay, in Q2, when I'm scanning a 0, that's good. I know that now I should accept because the least significant bit is a 0. So I transition to an accepting state and I write stuff and move stuff. It's irrelevant. I don't care what happens over there. On the other hand, if I read a 1 bit, then I go to a reject state. In our example, it was a 0 bit, so we go to an accept state. Okay, so when you need to program up a Turing machine, you have, of course, first of all, to have the intuition or think about this, but that may be relatively simple for you because you're used to programming. It's just another language. It shouldn't be too hard. It's then usually easiest to create a state diagram and finally write down the transition function completely. If I wanted to complete this exercise, I have to have here 3 rows for every state. I would need 3 more rows for Q2, and technically I would even need 3 more rows for each of QA and QR, although they're perfectly pointless because you never transition out of them, but the transition function requires us to write them. Okay, that is our first Turing machine. Now, it can be fun to play around with Turing machines, and one way to do that is to write a Turing machine simulator. We've kind of done that. If you remember this exec code that we wrote some time back, it is a Turing machine executor, But you can find these things on the internet. Just go search for Turing Machine simulator or something like that. And uh, it's kind of fun to play with these things, but they will look something like this. So here is this website, morphet.info, and it shows you a Turing machine. You can program it. So this is a language in which you can write the state transition diagram, and then you can run. So this language is one thing where it checks if the input string is a palindrome, and when you hit run, it'll show you where the head goes and what happens and so forth. Again, it's kind of fun. There are actually quite a lot of these. I found this one. Again, you write some code and you can run it. Here's one where it'll show you state diagrams. It'll show you the tape and what happens on the tape. And here you can, again, write code. You can actually program these things. This helps you understand stuff. Okay, end of that.